I have the pleasure today of introducing Emre Ertin. He's an associate professor in the Department of Electrical and Computer Engineering at Ohio State University. And he's also a principal investigator at the Davis Heart and Lung Research Institute at OSU. He's going to talk today about some of his work in wearable sensors and data analytics. He actually is the sensor technology lead for MD2K, which is this mobile sensor data knowledge center that is run by the NIH. It's a center of excellence. He's actually done a lot of work previously with a bunch of DoD-funded research, and he's gotten now into this wearable space over the last almost decade or so, and he's going to talk about that space today. He's been funded by a lot of acronyms, NSF, a lot of the Army Institutes, the NIH. And so today I'm excited to hear about some of this work he's been doing with wearables and sensing and data analytics in general. So thank you very much and welcome.
All right. Yeah, I thank Dave and Lisa for inviting me here, to the cute town of Dartmouth. I was just telling David that, I came in, the town looks like, for the people who've seen the movie Back to the Future, like the town square, the clock tower, the library, it's the exact replica of it. So you guys are lucky. Let's start with the talk. So, people in this field who are like me are interested in, improving the quality of the healthcare delivered to patients through better diagnosis and targeted therapies. So, whenever you want to make something better, you want to first analyze, what does work and what doesn't work, right? So, if you look at like our healthcare expenditure, everybody says it's expensive, U.S. is the country that spends the biggest proportion of its GDP. But where are these dollars going to? So if you look at like overall our healthcare expenses, 84% of it goes to chronic care. And in the Medicare world, 99% of it goes to chronic care. And, specifically, like, what are these chronic diseases we're talking about? So congestive heart failure, the cost leader, a patient costs the system about $41K per year, every year per patient. There are two codes there. The 9,000 is the actual costs related to congestive heart failure for that patient. But there is, another one, all these other costs for the tests and the medication, etc., that add up to that. And we go back, the coronary artery disease and diabetes, etc., are basically loading the system. You, me, getting, a physical once a year, that's not making the dent here. So if you want to make an impact, we have to make impact on this domain. And, another way of looking at it is saying, hey, those are the diseases, but, how did we come to those disease spaces? So people, who are more clever than me, looked at this problem from that side, saying, hey, what are, these health behaviors? How are they contributing to deaths in the United States? And if you look at it, tobacco, for example, smoking, contributes 18%, is responsible for 18% of the deaths in, poor diet, alcohol. These are the killers. As a father, I'm always worried about, vehicle, making traffic accidents. That's up there. It's not even a issue, if you just think about the long-term aspects of, life. So, what things are going wrong? So if you look at it, the medicine has been focused on treating the disease after it occurs, right? So you get to go to the hospital when you are sick, and your doctor most of the time sees you for the first time. So he doesn't know how you become to that disease state. And, like most of us, like it or not, you use most of your healthcare dollars in the, last 6 months of your time with us, and trying to beat a disease which is very hard to beat, right? So first we see that, we want to be more in the preventative mode and predictive mode if we're going to do those things. And plus, when we get a treatment, it's largely based on population averages. So, you go to doctor, for you, it's not you, but it's that disease that it's treating, so that disease class. So I have a few examples here. For example, congestive heart failure patients cannot maintain their hemodynamic pressure. Their heart contractility is not strong enough to push the blood and produce enough pressure. But, what's the standard care? They weigh themselves every morning, thinking, hey, maybe that's an indication of lung water, which is a result of this pulmonary pressure drop. But, if you just look at it, people, there's a lot of patients who won't see that change until 2 months later, but their pulmonary pressure already dropped. So these are showing patients who are okay as far as the weight standard is concerned. So they feel they're okay because they didn't see that jump, but their pulmonary pressure dropped down. So another famous example that people give is, the diabetes is mostly diagnosed based on hemoglobin A1C level, which is a sort of a months of average of your the glucose levels in your blood. But you look at it, everybody on the same A1C level is the same to your doctor. There is a certain guideline, and you look at that number. But you look at it, even same people, which has, different people who has the same A1C will show different trends over time with your blood glucose. Some of them will be even, some of them will peak and come back, and that's what leads to disease. So if we're gonna do better, the premise of the precision medicine is basically first to be in a preventative and predictive form. And how are we gonna do that? We will be able to only do that if we track people's individual health while they are, healthy, and do real-time analytics so that we can have personalized, actionable health information that we can use to improve the quality of care that we deliver to patients. And while we do that, we don't want, it's going to be just the doctor and you are a patient. You'll do what I do. We want them to take personal responsibility in their own healthcare, empower them with data, so that it could be a participatory process. So that's the promise. And the question is, why is it now? Why is it a good time now? Why didn't we do it before? So one reason is now we have all these sensors available to us to measure the physiology from different aspects. So we have wearable sensors for ECG, respiration, motion activity, how much you are sweating, admittedly, they go from dorky to more dorky on the variability scale. But yes, we have a potential to see the physiology from many aspects. But that's just what's going inside, right? We talked about behaviors, tobacco usage, drug usage, eating, overeating. So these are not shown directly in the physiology, but we like to understand how they are affecting. So, the way we work is, although these sensors are measuring your, motion or physiology, they inform you about behavior as well. So, for example, one behavioral measure is how much you are stressed in a day. So, the stress is a sort of a tension between between the two systems in your autonomous nervous system. And, if you have the physiology, and we can sort of make machine learning and, other statistical models and get biomarkers. And those biomarkers could be like the eating habits you get from wrist motion, or, the nerve sensors that Dave is making about chewing behavior. We have smoking habits, again, from respiratory patterns we can sense. Stress is about how your system is activated. And obviously physical activity like the Fitbits, etc. of the world. So, and we think if we have this biomarker, digital stream of your life, maybe we can understand the core causes of chronic disease and push you to healthy behaviors. So our research has been so far has been on these markers of finding. How can we assess craving, smoking, stress, and illicit drug usage from monitoring the motion as well as the physiology of a person. So I want to sort of start with, one example, so that we sort of understand how things are working and what do we need to do to go to the next phase. So we've been working for on the measuring of stress for a long time. So the idea is, build an ambulatory lie detector to understand whether, how your stress index changes over time. So we have a, system where we can measure EKG, activity, respiration, and then we extract features from those and try to see patterns of stress. And you are going to say, hey, that's not even like something measurable. There's no device for it. Well, how do you know that you are doing it correctly? So fortunately, the stress experts in our group have developed this battery of tests that are known to produce stress on people. So for example, you come to the lab and we ask you to give a public speech task. And we give you impossible ones. Do we give you one that says, hey, tell me about the precise economic effects of greenhouse emissions in China on U.S. steel industry or something like that. So, and then we say, hey, by the way, we're just going to tape you, and, we might put it on university TV, just to see how you do. So, and the idea is you look at, I don't know whether you can see it. So the top green shows our estimate of stress activation of the body based on that physiology. And the first test is the speaking test, actually. The speaking task starts about the middle of that stress. There's a lot of stress that happens before. The guy is thinking, hey, what should I say? How bad is it going to be? And, you begin to see that stress pattern. So that's one particular with something about mental. We give them arithmetic tasks of, do mental arithmetic on their head. And then, sometimes negative feedback. So I don't know, the guy before you was doing so much better than you. What's wrong? That produces stress. And, I found out that, suppose I'm good at math, still you feel like you can do better. Under that condition, no matter how you're good at the task, you still are impressed. We asked them to put their hand into ice bucket to produce pain sensation without, long effects later. So, we sort of, and asked them to do a treadmill task. So we see these patterns of stress and then try to identify it when they are up in the wild doing their business and try to see if we identify similar patterns of stress in the sensor data. And, although these are sort of sport vector machine models of this, but I like to know exactly, what is the mechanism we are seeing this stress. So one mechanism is this called heart rate variability. So our system, that modulates our heart rate is the autonomous nervous system. I don't tell my heart to go to a certain rate, right? So in this autonomous nervous system consists of two subsystems, the parasympathetic and sympathetic. One is like the gas, the other one is like the brake. So unlike like a car where you want to go 60, you just press the gas. We do both of them, gas brake at the same time, trying to, maintain that 60 speed. And, that tension between those systems manifests itself in how variable your beat-to-beat pattern is. So if I'm beating right now, say probably here now, 90 or so, now it doesn't mean, I'm beating actual precise uniform intervals. Sometimes shorter, sometimes higher. And that variability suggests my gas brake system underlying, trying to say, stay calm, it's only 40 minutes left in the talk, trying to feel it. So, therefore, we need to be able to analyze the differences, in the R2R intervals and the differences of differences to assess the variability. So, and usually I'm not used to speaking so large crowds, and I will ask, okay, which one is the healthier one here? There are two people with different variability on the top and below. And, which one do you think it is healthier? Bottom. It's actually the top. The top is a teenage, 18 to 20-year-old person, and this is somebody much later in their stage that has actually aged the system. So the way it works is, when you are young, you are more agile. You can, respond to 60 to 80, very agile brake gas system. When you are older, you press brake and gas at the same time and hope for the best, it will work. So, but no matter where you are, what your baseline is, when you are under stress, you up your, heart rate variability. And in order to do that, we need sensors that will be able to assess that. So, Back to the Future, very, appropriate for this town. But so this is something we did in 2010. And it was basically our first sensor that's really looked at physiology from multiple aspects. So it's a 8-sensor EKG respiration, 3-axis accelerometer, all built into a small package, and it streams data to a cell phone a week on a single charge. And then we use this data because it does at least 3-lead EKG quality data. We can begin to look at these beat-to-beat patterns. So that was our where we were in 7 years. So hopefully these examples gives you the feel of, hey, if I can sense physiology in the field, then I can enable large-scale research because I can look at a large population, and maybe I can begin to learn about potential causes of chronic disease. But while we want to do that, we don't want really our subjects to look like that. So we want to be like somewhat socially conforming. There's a note. I always tell this story. And I was building this band. I had a partner in University of Minnesota. He's a stress expert. So I built this from electrical engineer. I'm very proud of its battery life. 8 years, I say, we have this custom communication protocol that can extend the thing. And he looks at it. The first thing he says, we are doing a 7-day study with smoking, and he's thinking about variability of the device for the smoking population of 7 days. The battery lasts 7 days. So he said, can they shower with it? And I was taken back because I never thought about this aspect at all. And I'm like, it's only a 7-day study. Do they really need to shower? And second of all, who smokes in the shower? Is it an epidemic that we need to target right now? You can talk your way out of some of the problems, but we understand if we're going to do an impact, we need to bring our sensors to the next level. See, to make them more. And what are some guiding principles to doing that? We needed them to be minimal burden. We needed them to be continuously active because we never know where you're going to be stressed. If I'm sampling once in a while, how do I know that I sampled at the opportune times? We need to be robust. They need to be out there in the field. And, less black boxy is better. We need clinically useful, and we want to be able to understand the physiology, biology, psychology behind those machine learning techniques to be able to go back and say, hey, if I'm going to make a new sensor, which part should I make it more sensitive? And, people like me and Dave who develop sensors, a lot of the time we get the question, hey, I have this Fitbit here, it does very well. What are you doing for me? So, we want to understand, we are in the business of science, and, these lifestyle sensors are beautiful. Sometimes they are built into the phone app. Why do we need even a Fitbit? You just carry the phone with you. So this is the easiest thing you can ask to an activity monitor. So people done experiments, treadmill, constant speed, 500 steps. Very precise thing. And you hope that they will produce 500 when you volt on it, right? So you looked at it, and these are the results for the different sensors. First we see the answers vary widely from 300 to 500, and I think that's okay. We are working in the wild. There is going to be errors in these things. We have to accept it. What is not okay is you look at the Fitbit, you come home, you open the box, it will never tell you, our step count is plus minus 10% correct. It just was have no guarantees. And compare that to the cheapest blood pressure monitor you buy from Walgreens. You open up, it will actually say plus minus 10 millimeter mercury correct because it's governed by different regulatory agencies. And therefore, the conditions on them are quite different. And some of them are even more shameless, like the Nike field. What does it mean I got 200 field? I can't even assess it in my studies. And before that, people who worked in this field will know the actigraph. That was a accelerometer. It produced this very scientific term, ticks. You get 100 active ticks. And believe it or not, it still today is a standard because people took that ticks and mapped it to metabolic rate. There were studies done that transformed that. Nobody still knows what ticks are, but it's something you cannot really understand even to make a confidence interval. So if we're going to use it in research, we need confidence intervals on these sensors. We want to be able to put on, hey, when this sensor reports this is the confidence interval. Plus, depending on the context, those confidence intervals are changing. Right now I'm talking, and I'm in relatively less motion, so obviously the counts will be much more accurate. But if I'm in random motion, probably it changes. So if we're going to make sensors, we want to be able to make the sensor assess its own quality, and we want them to be more variable, of course. So fortunately, this is not the only way to skin a cat. There are more ways. But one, again, look at it, you shouldn't look at it as, sort of, hey, just another modality, it will produce the same information. The physics tells us the quality of that information. You look at the EKG, it's the polarization of the heart, right? So, and it's an electrical process, very fast in terms of bandwidth. So therefore, sharp peaks, that heart rate variability measure will be very accurate in terms of millisecond accurate heart rate variability measures. Here is somebody wearing a PPG sensor, reflectance-based, and this is about blood flow, right? So it's fluid mechanics, a slower process to start with. Plus, so here I plotted the EKG on top of a person wearing it on left and right wrist. And you can see first, even the same person, how much variability there is between left and right. Plus, the peaks, if you can find them, are not very sharp, right? So the width determines how well you can do it under noise, and it's not clear. And on the right is a new sensor from our group, which essentially is a micro radar sensor that you can apply to yourself, and it images inside of you and sees the heart, believe it or not, inside of you. So that gives another mechanics. It's motion inside the body, which means it's different in terms of quality, and we'll come to that. So how do we make it, perhaps better is, a lot of the lifestyle sensors use a green LED. If I'm making my own sensors, I can first assess the quality, plus I can produce additional channels. Putting a red LED, infrared LED together, I get more information. Here I superimpose red, green, infrared from the same. None of them are clean, but whenever they align, that suggests there is some underlying common physical. Maybe I can take advantage of that. So that's one idea. With the radar, too, I can sense it using one transmit antenna and one receive antenna, or I can use multiple antennas and make an array, get a stream of measurements on multi-dimension. So, but if I'm going to use that, EKG, if anyone worked in EKG, there is a thing called Penn-Tompkins algorithm from the 70s, which is essentially filter the signal, square it, threshold, whatever. So it has but it's geared towards that single modality, single line, 1D data. Now we are having these streams of data multidimensional. So we want to have essentially beat detectors that work in general. So little bit math. I didn't think I made a promise otherwise. But anyway, so the idea is, hey, I know that if I'm looking to a window, there are two possibilities. Either I'm seeing just the background variations in the signal, which is modeled by S, what we call interference subspace, plus noise. And then whenever there is a beat, I'm actually on a signal space modulated by the columns of H. So this is my vector. So X is a vector, and I'm trying to write it as a linear sum of basis vectors that I understand. And they are related to, of course, what I'm looking for. So if I'm looking for an R peak, so the signal subspace captures the R peak shape as well as its variations, because beat to beat, there's going to be little variations depending on how I'm looking. So I captured that by different columns of H, doing essentially like a PCA of a R peak. And S is anything that I couldn't model. One is the long-term variations in the bias, the DC level changes. I'm not interested in it. I put it to the signal space. So people, in the field would know that, Scharf find these detectors called match subspace detectors, which takes the match detector, which is sort of correlate and dump feature, to multi-dimensions. And the idea is saying, hey, if I receive a signal vector, can I explain by the vectors in H Is it parallel to H or is it orthogonal to H? So you measure that angle. Whenever you get aligned to your signal subspace, I must be close to my signal. Here is my peak. So the nice thing about this is it applies to any dimensions, any modality, as long as you can write your signal as in this PCA representation. The other thing, we talked about it, I want these devices to last longer, which means I need to control the bandwidth, how much power they do. If I have 8 channels streaming 512 hertz at a time, my radio is not going to support it, or my battery is not going to support that, right? So I need to be able to sort of find ways of compressing. So one, in the past decade, one, a tool that comes to our toolbox is compressive sensing. So the idea is I get a signal vector, Y, and these are the samples from the different channels, put together, and I just take linear projections of them, random linear projections. I invent vectors, I take a linear projection, and I just report the result. So Y is on the right-hand side is the raw signals, and I have a compressed summary of them. The good thing is, of course, I know how I compressed it. I know which random projections I took. And remember our detector, which measures whether I'm aligned in the signal subspace or not. I can directly perform this matching part in the compressed samples. So a lot of compressed sensing, you look at the literature, they try to first decompress. They try to reconstruct the signal. So I receive on my receiver the Y compressed, and I try to first get to Y and do my old school signal processing on Y. Here what we do is something different. I'm not interested in Y. I wanted Y because I wanted to find where the peaks are. I can do peak search directly in the compressed domain. And the good thing is you can show that you get actually higher compression rates from the theory if you are only interested in the peaks. You ask less. You say, I don't want the full signal, I just want the peaks. You actually can compress it more, which means less random projections to produce. And we were able to, apply this to 512 hertz ECG streams, and we were getting 30 compression rates. People who are familiar in the compressed sensing, if you are in the reconstruction business, 3-4 is the compression rate you get. So here we ask less, but we can live with more compression. And usually here, a good question would have been, I didn't pay anyone in the audience, so no, I have to ask myself. But hey, but this is like giving me just the R peak. What if I was interested in another ST peak, other peaks, etc. But remember, our projections are universal. I didn't do anything to project, for example, to my signal subspace, which a lot of wavelet-based stuff try to do is, they know what the signal subspace looks like, they project to that. We just did random projections, so which means we could search other peaks as long as I know his signal subspace, which is different than R peak, and I was able to do T peak, P peak, etc. Detection from the same exact stream. So these are universal compression schemes that are lightweight, easy to do on the variables, and you can do it. So what happens if you apply it to this 3 LED screen? So this is the left wrist multi-LED data, which I'm wearing. And here are the GLRT process out of it. We can see that I certainly missed 2 peaks. I'm close to missing one here, and I certainly miss another one. So it's not perfect. Given the noise, even 3 channels, you are missing it. I'm wearing this sensor right now, and I can tell you, unequivocally that no sensor can actually do well when I'm trying to do this motion, except ours. How? Because actually it's been calculated, the other one I wear on my right. So, and I'm not joking, so we ask our patients to do both, okay? So we wear 2 sensors, and here I see that bringing the right wrist data in compressed form from the other sensor, I was able to fill the peaks, right? And I get much better R2R interval measurements, okay? And this is not as simple as just having 2 sensors. So if you wear 2 Fitbits, you average 2 bad answer, it's still bad answer. You need to be able to do these things in the, sort of closer to the raw data so that your detectors work on the combined set, not first get the detections and then fuse them. So that's still, the sort of the commercials where things work, where, things are not hard. You go to the field, it's a different animal, right? So this is the lab data where, I was going to say, it's a bad joke. I happen to take cocaine, but yeah. So a subject goes through the cocaine trial where, it's been administered at different dosages. And, we are tracking. This is the lab, and then this is the same subject out in the field doing his business. So we see that, first, the variability in R2R intervals increased. And this is artificial. Nothing changed for this person, except that my detection begins to be more noisy, and I'm introducing additional variability that is not real. I'm also detecting these missing peaks. Whenever I miss something, it becomes twice the interval, right? So those are the long intervals that don't exist, but because I'm missing it. So I suggest something is wrong. What can I do, to do better? When you work in this domain, you understand no answer is the right answer. In the sense that, given this noisy stream, there are many potential likely answers, potential likely locations for those R peaks. And I'm interested in all the answers, right? Because if no one answer is correct, it's a better approach to calculate multiple and then take average of your statistics that you are trying to do. So our subject has been, hey, can I take a stream of data, the Y in the sense, and I can produce state numbering of this. So here's the stream, and I'm trying to, then all these little peaks are distributed between no peaks and R peaks, that I'm after. And if I can do that, that's one set of answers. But there are other answers that are equally likely, given my noise model, etc. And if I can produce other streams of these, I can take average of those and I can do better. And, the standard machinery for this is this hidden Markov models, right? Because it says, hey, if I'm here, what is the likelihood I will get another R here? None, because it's close together. Nobody's heart beats like but and the but. So, which is, this is a not likely one. So the hidden Markov models is, although no state is known a priori, it tries to estimate states that are consistent with each other in terms of the distance. The problem is, if you just take the standard, anyone who's familiar with HMMs is clear that, if you look at the Markov model, the state transition probabilities are geometrically distributed. So you don't control the distribution, it's geometric control, you can control the mean. But it's not like that. We are actually beating in a very, predictable fashion. If I'm beating, 60 beats per minute, I will be between 0.9 and 1.1. That's the probable region between R2R intervals. So that's not a good model for us. Now, fortunately, people that are more clever than me just figure out a way to augment the model. So the idea is, hidden semi-Markov model is they get a new state variable, not just R peak, no R peak, but each time you come out of an R peak, you draw a state sequence called duration sequence. You take a duration sample. It could be sample between 0.9 to 1.1 second, let's say, and you count it down until the hidden Markov model starts at end. So each time you go to a new state from R peak to no peak, you take a counter that suggests the likely duration of this R to R peak. You can write it as a graphical model, and you have two states basically. One is counting down. Whenever RT is the duration, which is counting down until it goes to 0. Whenever it becomes 0, I change state, either to R peak or P peak or N peak, whatever it might be. And again, remember, I'm interested in all the answers. I ask a lot. Fortunately, hidden Markov models are good in terms of calculating probabilities, posterior probabilities of any labeling of that peaks, given the data. So, the standard people who done speech, etc., know that there's a famous algorithm called forward-backward algorithm. What it does is, if I know the answers up to the point T, can I calculate answers beyond T? And so if I knew how the probability of each one of these sequences up to t to be r or none, can I calculate a point in later time whether it's a peak or not? And it goes very simple logic. If I'm trying to assess this t point, I go back and say, hey, maybe the point that was r1 away from me was a peak, and I transitioned from that, and I just calculate the probability of doing that given the data. Or maybe there was a previous peak that was the r peak, and I transitioned from that with a larger duration. So you add those probabilities add up to the probability of observing a peak at a certain location, given that I calculated all the probabilities of peaks before. You know, to cut the short story, so one can calculate these forward-backward samples and calculate what is called this Viterbi solution, the most probable sequence. You know, given my data, given my duration assumptions, I can get the most likely labeling of this sequence. But there's just still one answer. Remember, I was asking for joint distribution of all answers. But, you know, maybe, you know, I'm not going to be able to even capture the whole distribution. But I can ask for less. How about I sample from that distribution? How I just sample from the likely sequences? So one can actually do that by doing a forward pass and what they call backward sampling. So I go forward, calculate the probabilities, and I get a sequence of likely values on the back edge trying to label mine. So now for the same exact sequence, I get different answers. And you can ask what happens, results, right? So here, it's sort of hard to answer. So the y-axis is realizations, and x-axis is time. And whenever something is white, okay, it means it decided to put a peak there in that realization. I'm having 1,000 answers here. Most of them are the same, because that seems to be like the solution in this case. But look there are in cases where this guy is switching between calling this a peak and this a peak. So, you know, you look at here, some of them are lighted here, no light here, no light here, which means it is thinking, this is a solid peak here, I'm not sure. Sometimes it chooses this one, sometimes it doesn't. And it's all consistent in the sense that whatever you choose here will affect the entire sequence because it's a joint sampling from it. Similar issue arises here. You have samples here, it's alternating between these two peaks, trying to figure out which one is the correct answer. And again, the mentality is no answer is correct. All answers in this domain are likely, and we have associated probabilities. And once in a while, it also draws crazy sequences. You know, this is a sequence where it decided not to place a peak here. It placed a peak here. He knows that it can't place a peak here because it will be too short. And it decides to shift everything to the right. And, you know, that's another potential solution. Apparently very unlikely because out of 1,000 realization, it only chose that answer once. But we put it in the pile. And we calculate. So, result heart rate tracking. So this is Troika. It's an algorithm developed by Samsung Research. Okay, we are using their data. This was actually a signal processing cup challenge 2 years ago. So the red is somebody's on a treadmill going from 92 to 160, right? So, and the red is the correct answer because he was wearing a EKG leads. So we know what the correct, green is the Samsung answer, state of the art, believe it or not. So, and you know, the cup, nobody was able to beat Samsung solution at the end. So, and it's 3.94 beats per error, you know, so which means it makes an error of plus minus 4 beats per. When you look at your watch, instead of 120, it could be 124, 170. And our answer, using their data, not bringing our own sensors, just the algorithm, the sampling idea, saying no answer is correct and averaging the answers gives us a much better result. Our error is less than beats per minute. So, you know, there are some, you know, lights at the end of the tunnel. You know, I always tell my students, whenever you show the good results, show the bad results too. So this is the part. So this is saying, hey, if I have this R to R intervals, remember thinking about my stress level, there is in there low frequency variations, and there is high frequency variation. We do a superb job. This is the spectra of those R to R cinemas. We do a superb job of catching R to R intervals and their variations in the low frequency regime. But it seems like the black is our answer, red, so here, So the red is the correct answer, black is our answer. We see that we invent additional high-frequency variation by our graphical model. And why is that? Because, the heart is actually a biochemical thing. So where you have the sinus node, whenever you want to change it, actual chemicals flow in that sinus node and changes. So it's very slow. There is correlation between R to R peak in the previous period, and so there's a plot of that. Since our model didn't have that, we didn't predict that slow variability and didn't. Once we put it back, we do much better results by modeling it. So far, I try to say, hey, if I have little more channels, 3 channels on one wrist or 6 channels on one wrist, and if I do probabilistic estimates, I can do better. But people presented, they say, okay, you do 2 watches, fine. So going to a completely different direction, hopefully, a little more interesting is, we said, hey, we want people, take showers. So we want to be able to have them wear sensors that are, that you can wear over your, garments and, to be able to sort of stable. So under NSF funding, we looked in this bioradar application. So what we do is basically, we created a, small micro ultraviolet radar platform that uses 0.5 to 3.5 gigahertz to send waves into the body and looks at the echoes. And it has MIMO diversity, meaning multiple antennas on transmit, multiple antennas on receive, to be able to assess the body. How does it work? So you have the transmitter sending a tiny pulse, short pulse, high bandwidth pulse, and it goes to the body. So, and here's a, cross section of a graduate student. So we, before the candidacy. So it's each interface, air to fat, fat to muscle, muscle to bone, provides a reflection boundary. So what we see is basically, when you send one pulse, you get multiple pulses indicating the different tissue boundaries it hit. And you look at it, this is the sort of thing you see on the sensor side. So this is range, meaning sensor is on the top, the body is into the body, and we see different reflections. And this is the time axis, right? So you see, the skin level, not much variation, time-wise. But you go deeper, you begin to see some patterns because internally things are moving, meaning that surface is moving and coming in and out of the range. One can, say, hey, that's a good problem, but, some people will say, hey, let's stop here and maybe try to put a machine learning algorithm to figure out these patterns, right? So that's possible. I think that the information is there if you're after RP detection. But we said, hey, we want to understand a little better because, I can ask students to do anything for me. So, I want to know what's going on, right? So, and I always say, can we write it down? What is it really? So basically, X is, what we are after. We are trying to reflectivity profile, where those layers are. And Y is my measurements, obviously. P is what the wave I send. People say, don't you know? Why don't you plug it to the, network analyzer and measure it? The thing is, when you use it in the network analyzer, it's quite different when you are using it to the body. It couples, the antenna detunes. So what you end up sending is not what you intended to send, and you calibrate in that. So as far as this purpose was concerned, P is an unknown, what we actually send into the body. And, Q is just essentially describes the geometry of the reflectors, etc. And, P is the pulse when we convolve it with the reflectivity profile gives us an answer. And we said, hey, I want both. I want to know where the reflectivity is, where the X's are, where the layers are, and I want to also know the P, which is the pulse I sent into the body. So you can write it, okay, I want to explain my measurement by a combination of the pulse and the reflectivity profile. And I want it to be, a certain bandwidth, because I know I didn't put 10 gigahertz into it. I only generated 0.5 to 3.5. So that's the bandwidth constraint. I know the pulse power is constrained. There's a certain constraint. And, I only want to look in certain range. So, fortunately, you can do an iterative algorithm to solve this problem that, looks difficult. especially if you take sparsity of the signal, which is another cornerstone of compressive sensing, is saying, hey, I can solve for all x, but I can find x if it's sparse. Remember, there are only so many layers. It's not everywhere. So what you end up getting is you get the measured backscatter data, and you get the reflectivity profile. These are where the layers are that you are measuring. So from the raw data, I was able to recover where the reflectivity. Plus, I was able to get an estimate of the pulse I sent. This apparently is the pulse. That makes sense, which means this is the pulse I sent. And then I can take this data and produce R-peak estimates from this data. I can throw it to match space detector that we looked at. Yeah, but I see a lot of faces here. I'm not impressed. Okay, can we do better? So the idea is, hey, that was just one antenna, one receiver, right? So I can put multiple antennas and look at the heart in different angles. And I can put those reflectivity profiles together to produce an image. And this is sort of what it looks like. So now you say, okay, maybe I believe there is a heart there. Yeah, the guy has a heart after all. So, you can see the pump, the actual action, much easier to actually get a detector running on this fused space. And still, it doesn't seem like a lot of, consistency. And the reason is, as the heart is moving, we are using very little power to do this imaging. So each frame is very little power, a lot of noise. So one idea from the MRI literature is what they call cardiac gating. Your heart looks the same, every time it beats. So if I can freeze your heart at the same exact time, 0.1 second after it beats, 0.1 second after it beats, and I can take data from multiple heartbeats, put it together, and get SNR increase. So, and this is the sort of getting one heartbeat image. So this is the sort of image you get once you do that sort of imaging, cardiac gating, putting SNR back where it is. And again, some of you, I think, the future land, I guess I'm a movie fanatic guy. So the future land, I think the little guy comes and says, to the table, it's a science fair, I believe. It says, here it is, it's a rocket pack. And the scientist looks at it and says, what's it good for? It's a rocket pack, like, what do you mean? So it's similarly, we have a cardiac imaging, which I feel is just amazing just from, just looking at it and be able to appreciate your heart, that it beats 24/7 for you. Maybe we'll take better care of it. But of course we can throw, our detectors, and this is the R2R beat detection we got. The blue is from the easy sense, and the red is traditional ECG. We see alignment, we see quality of the peaks, right? Still, it's motion of mechanical bodies. So it's not high frequency. So the peaks are still not, as sharp, but that's physics. We can't beat physics by just throwing more, acronyms of, LASSO, S1 to it. So, the good thing is, since we are beamforming, we can beamform away from the heart and look at the lungs. We can get the respiratory patterns. So this is sort of looking at how the lungs are moving on the side to the heart. So it's a good one. So another thing, we were talking about Dave. We realized that, whenever you actually sweat a little bit, your shirt gets wet, the sensor doesn't work that well, okay? And, when my students told me, they said, maybe that's a good thing, it's sensitive to water. So we said, okay, what is it, why is it happening? So each time, this electromagnetic wave passes through different tissues, fat, muscle, etc., there are two effects to it. Loss tangent, it gets absorbed, okay? So some of the energy doesn't come back because it's absorbed by the molecules. And it changes based on the different tissues. More important, whenever electromagnetic wave goes through you, it slows down. And how much it slows down is related to this thing called permittivity. We see that things are changing different permittivities, right? The focusing we used to do doesn't work because now there is more delays in the system. So the idea is, can I use this feature to be able to assess lung water content? We already talked about congestive heart failure patients and not being able to maintain their lung pulmonary artery pressure, and as a result, accumulate water. And this is how the progression looks like these days. You are stable, and then all of a sudden your pressure changes. Your heart doesn't have the same contractility. It doesn't push enough blood. Your body is pretty clever. First thing it does, it tries to beat a little faster, okay, so that it still supplies the blood. Second, the arteries get a little stiffer to provide more flow to be able to, compensate for it. But at one point, it loses that battle, and you begin to have impedance changes. The tissue begins to get water from the interstitial space to the tissue itself. And then, if that water becomes enough, you get a weight change because you have water in your system that you didn't used to have. So the standard care is actually on these two spectrums. There is a sensor called cardiomems, golden standard. It's you brought it with a catheter to your pulmonary artery and drop it there. Believe it or not, it stays there and it measures the pressure. So of course, you see it the first time the pressure changes. This is a 2-month period. You see it very early. Perfect. And you can't really beat it. Nothing can beat a sensor that's sitting on what you are trying to sense. And this is the other end, where the classical, the standard care. You ask people to weigh themselves every morning. If there's a 3-pound difference, you say, come to the hospital. There's something off. And we can understand a lot of false alarms, a heavy meal, something can trigger a 3-pound. Or, it's so slow. It's 2 months by the time you reach there. It's a lot of time too late. If they can catch early, they can do diuretics. We said, hey, okay, maybe our sensor can, intervene somewhere in between. We are not going to do it because we can begin to see impedance changes. When the tissue begins to have different properties, we begin to see that. So, and the idea is basically we ask them to a daily measurement. This is a very slow process. They don't have to wear it, become dorky, but they can just do their little measurement once a day. And, they hold it. It sends electromagnetic waves inside the lung and looks at the echo. And then tries to figure out this permittivity coefficients to figure out whether the lung has more water or not. And we did a rather pilot since, in the early stages, I asked the students to put me in an inversion table and, flip me around so that I get blood flowing to my lower, segments and try to see whether we can see that change. It gets old pretty quickly. So we did go to a real pilot with the Wexner Medical Center, where 20 CHF patients who are admitted with lung water. They are in the hospital trying to dry their lungs, and we are monitoring their drying process. With the hope that if we can figure out wet to dry, we will be able to perhaps do the dry to wet detection. So here are different subjects. The first 12 subjects, again, show the bad data. The first 12 subjects, things didn't work very well. So starting with 13, we got what's wrong. So you make these sensors, you understand that, they warm up. And, as they warm up, the phases that we are trying to measure changes. And we find out that depending on when you put on, how much you wait between the measurement and you power on, affected the measurements day to day. So now we put a calibration loop inside it so that we can, sort of take out that effect. And starting with 13, we got touchdown. So, the blue here is showing basically whenever there's a significant change based on the zero baseline. We were able to see all subjects, showing a change in the right direction. Plus, I think more importantly, because there is new technology from a startup that tries to do the similar thing by doing a measurement, a pass-through measurement. They have a sensor in front of you, and they have a sensor in the back of you, and they do a pass-through measurement. Similar idea, unfortunate for us, but doesn't matter. So we do echo, which means we have an idea of range. So not only we see water, we know where it is. So we see, for example, accumulation in 2 compartments, intravascular versus extravascular. And whereas the other technology, they just see the sum. They can't see where things are actually accumulated. So this enables us, perhaps, we are saying clinically, this deep water is more of a problem. If you are doing close to your skin, some edema, that's not a life-threatening emergency. So perhaps this gives us a more clinical information, but we wanted to see if people can do the similar study on their homes. So we are starting with a pilot study with 150 patients 30-day post-discharge to see if we can figure out from dry to wet condition. And people take it home and they apply it to yourself. And then we run through 5 or so. I think we have like a 60% science, not a lot, but if you have seen these patients, it's not an easy life for them. So, but, we are out there trying to see if it works yourself. So I think I'm running, close to the time, although I didn't see anything else. So maybe I want to close. In this field, as you see, I like to get my hands dirty. So I finish with a quiz maybe. So one U.S. president, okay, has a patent. Okay, so does anyone know which U.S. president has a patent? It's on that patent there. I just blocked the name so you can't read it. Don't squeeze it. Okay. So it's Abraham Lincoln. Okay, so it's a patent to have, when a ship gets stuck on low water, to have a buoyancy to get it, floating again. So, and what's underneath? It is a model of that idea. Okay, so if people have been to Washington, D.C., National Portrait Gallery, if you haven't, I strongly recommend it. It used to be the U.S. Patent Office. And before 1910, whenever you submitted a patent, you needed to submit a working model, no drawing, just a working model, even if it's replica. So here are some, things you can see that a patent, a model, a patent, and a beautiful model. So everything. So, and it's in the 4th floor. At 1910, they ran out of space, so they said no more models anymore. Just give me the idea. But in this field, I think we make a lot of the time the mistake of we write one sensor, one paper. Okay, so I come from that. We even named our sensor. That sensor. This is Bob. His accelerometer works beautiful, but don't trust it for gyro. You write the paper in a way that it will, sort of don't highlight the gyro, let's say. Okay, so, but, in this field, we are serving clinicians, epidemiologists. So we have to be out there, sort of, in quantity, test our sensors in field. So we've been, really trying that hard in the past decade. So this is our radar sensor when it was first, imagined. Now, of course, this is never going to go anyone's home, but we need to go to it. But I can write a paper, believe it or not, with this one, no problem. But, that's not going nobody's home, right? So this is the final aim. So we try to make our sensors really useful, although maybe you don't get a paper out of it, but it's important to serve the community. This month, we are shipping 1,200 of our sensors to collaborators across the nation, as well as Dartmouth. Lisa is going to get some. So unless you try it, you will never, I feel, get the real impact of your work. And as engineers, I feel we are responsible, to show up for work. So I didn't get to do a lot of thinking. So we do a lot of motion tracking, gesture recognition through those. So this is me doing some act. If you can, toothbrush. I know in virtual domain, I look awesome. You can be anything in the virtual domain, red devil, whatever. So we do a lot of motion tracking. We do, try to understand how workspace, not just disease populations, but looking at, with new projects with IARPA, trying to see how office space behavior can be assessed. Am I a good worker, high performance worker? Because I know when you are late to work, because your accelerometer shows that you had a jerky drive and come up 9:05 to work. So, and I know exactly how many times you typed. I know how long sentences you use, how much you spend time on swiping on your phone. That's one aspect. The other thing is, I know how much stress you produce on the others. If whenever I see Dave, I get stressed. Problem is not me, it's Dave, really. So begin to understand troublemakers and people who make together. So I feel this is the first time we are looking to a general population, not disease, and trying to see some patterns. I think, there is some benefit of doing that. I want to close by saying, hey, I just talked about this. I'm here. I'm the sensor guy. I've been known as the sensor guy. And I do signal processing very close to the sensor. But if you want to do these studies, it takes a village. You need to have people who are good with phone software to be able to get your data, react to it, provide interventions. You need, cloud computing to be able to get to that data in mass and able to do it. And, I understand as individual researchers, maybe we don't have the resources to do that. So I'm part of the MD2K center led by Santosh Kumar at University of Memphis. So it's a multi-university collaboration. And the idea is to empower researchers who do this by providing the pipeline. So we give you the machinery, so you plug in whatever your thing is. So you want to do a study, you are only focusing on your part. So I encourage everyone to go to md2k.org, one of the 11 big data to knowledge centers of excellence funded by NIH for serving the community, not writing papers and just doing one at a time, to be able to do mass research. I want to close. I learned a lot from computing guys, but to heck with them. So these are the medical collaborators. That really taught me about how the physiology works, especially Larry, who passed away, who was very influential in our work early. I'm here doing the show, but the real work is done by the students. I can never get them to the same place. They don't sleep in the same schedules. But people, and thank you. I'm open for questions.